Hi, and welcome to a lecture on mutual coupling effects. In this case, we're going to be examining a transmitting array, and specifically a uniform linear array. A uniform linear array will make it easy to understand how these effects are coming into play and makes the overall problem just a little bit simpler to understand. So the array we're considering is this one, consists of n elements. The elements spacing is d, little d, and these are half wavelength dipoles. So the elements are half wavelength dipoles. We select half wavelength dipoles because we have simple expressions for the mutual impedance between these dipoles, which then allows us to compute all the mutual coupling effects that are relevant. The geometry is this one, where x is up and out of the page, y is to the right, and z is up. And we're going to be looking at a beam, a maximum gain beam, pointing in the h-plane. So we will be scanning a beam in the h-plane, which is this plane here. In other words, the xy plane, where phi equals 0 is broadside. The procedure we're going to follow here is the simplest one that you can imagine for a problem that includes mutual coupling. And what we'll do, we will impress voltages onto the dipole terminals. And we'll do that ignoring mutual coupling, but we're not really ignoring mutual coupling, we're just forcing the voltage to be a certain value at the terminals. Now, this neglects any problems that you'd have with impedance matching a transmitter, but again, we're trying to keep this as simple as possible. So we presume voltages, applied voltages, then we compute the currents in step 2 by calculating an impedance matrix, and then the currents will simply be the inverse of the impedance matrix, right, multiplied by the applied voltages. Once we have those currents, then we have everything we need to compute a pattern. So we'll be plotting the h-plane patterns. Finally, we'll examine the active impedances. Once again, these are the impedances, the ratio of voltage to current at each one of the terminals. We know those active impedances will vary as a function of pointing because the currents will vary as a function of pointing, and the active impedances depend on those currents. So we'll use the currents that we determine from step 2 to compute the active impedances, and that will give us an indication of how much difficulty we're going to have doing impedance matching here. And I'll point out finally that once we have these active impedances, then we can go back to phase 1 and figure out what the source impedances would need to have been to achieve those applied voltages. Okay, first scenario. We have 4 half-wave dipoles in this array. They are spaced by a half a wavelength, which is a pretty common choice. And the beam is pointing broadside. So in this case, red shows the result without mutual coupling. This is simply ignoring all the mutual impedances. And so you see the red curve is kind of the expected one, where you get a maximum. The side lobes are about 13 dB down or so, and so on. With mutual coupling, there's only a small change. The main lobe is only slightly wider, and the side lobes are slightly lower. Over here, we have a plot of the active impedances. The horizontal axis is the real value of the impedance in ohms. The vertical axis is the imaginary value of the impedance in ohms. And just to remind you, this red cross right here is the self-impedance of a single dipole in the array, because we know that the self-impedance of a half-wave dipole, a thin half-wave dipole, is 73 plus J 42.5. So if there were no mutual coupling, all the active impedances would be equal to that self-impedance. But since we have mutual coupling, we're considering it now, we find the active impedances are different. And for this particular pointing and this particular spacing, we end up with 2 values here and 2 values here. There are 4 separate active impedances, one for each set of antenna terminals. And we see they're quite different from the self-impedance. From this, you could easily figure out the reflection coefficients and the voltage standing wave ratio and figure out how much power is lost due to reflection as the transmitters try to apply power to the antenna array. In the next scenario, we again have 4 antennas, but now we reduce the spacing. We reduce the spacing from 0.5 wavelengths to 0.3 wavelengths. So we would expect the mutual coupling to grow because we would expect the mutual impedances to be somewhat higher. The pointing will remain the same at broadside. And what we see now is that the mutual coupling, the blue curve here, is showing a greater distortion with respect to the non-mutual coupling result, the result ignoring mutual coupling. That is to be expected. Furthermore, and again as expected, we see the active impedances vary by an even greater amount relative to the values that they had in the half wavelength spacing scenario. So we would expect a greater difficulty in doing the impedance matching, or if we chose not to do impedance matching here, we would find a greater amount of power reflected. By the way, these axes will always keep the same scale. So we'll always go from less than 40 to above 120 on the horizontal axis, and always minus 20 to above 60 on the vertical scale. So you can easily compare these results. The next scenario we'll consider, again, 4 elements, broadside pointing, but now we want to separate the elements by a greater amount. So now we'll go increase the spacing by a factor of 10 to 3 wavelengths separation. Now, of course, when we have such a large spacing between the elements, we will have grating lobes, or alias lobes, 2 words for the same thing here. So we have the desired broadside lobe, and then we have the alias lobes appearing here because, again, we're violating Nyquist with respect to the sampling of this aperture. So we end up with a bunch of extra alias lobes in this case. But what you see is, in fact, whether you include mutual coupling or not, we see the results are generally about the same. So mutual coupling has very little impact on this case, which is what you'd expect because the mutual impedances should be small because the element spacings are relatively large. And when we look at the active impedances, we see that compared to previous cases, they are much closer to the self-impedance. And we would expect this trend to continue. As the spacing increased, we would see generally that the active impedances got closer and closer and closer to the self-impedance until maybe you were 10 or 100 wavelengths between elements, and then they would be very, very close. In this next scenario, we again have 4 elements. We'll go back to half wavelength spacing, but now we'll steer the beam off by 45 degrees. So now the pointing is 45 degrees off broadside. And what we see right away is when we consider mutual coupling, we see there's a significant shift in the beam pointing. So we see that in the presence of strong coupling, the beam direction can shift slightly compared to what we expect. And of course, we also see that the side lobe structures get jostled around quite a bit. Also, by pointing off broadside, we now see what's happened to these active impedances. They've all separated and gone in different directions, so they are quite different now. Before, we ended up with 2 values being the same, another 2 values being the same because of symmetry. When the beam pointing is broadside, we would expect the active impedances to have symmetry between the left and right sides. But now we have no such symmetry, and in fact the active impedances all have different values, and you would expect that would be correspondingly more difficult to impedance match. Not just for this one pointing, but if you wanted to do a good impedance match for all possible pointings in the H-plane, you see now that you have a very broad range of possibilities you would have to account for. Again, this is called scan dependence. Scan dependence refers to the fact that these impedances are all moving around as a function of beam pointing. The final set of scenarios we'd like to consider here pertain to a 16-element array. So we'll increase the number of elements to 16, once again half wavelength spacing, and we'll go back to broadside pointing. And what you see is a very important thing to know about large arrays, is that the mutual coupling really doesn't make much difference in the near side lobes. In the far side lobes, it makes an increasingly big difference. So if you care about what's happening in the far outside lobes, the mutual coupling is quite important. But if you are only concerned about things that pertain to the main lobe and the first few side lobes, for a large array, mutual coupling tends not to be that much of a factor, at least in terms of the pattern. Now, when it comes to the active impedances, that's another story. What we see for a large array in broadside pointing is we see these are the active impedances, and they are, again, quite different from the self-impedance, but at least they are tightly clustered. These two active impedances, by the way, are for the outermost elements. So it's quite common to see for a large array that the interior elements have approximately the same active impedance, but the outermost or the edge elements have a significantly different active impedance. And of course, what we said about scan dependence in the n=4 array also applies here. So now we'll scan off to 45 degrees. Here is the beam now pointing at 45 degrees. And we see things are getting a little bit jostled up now in the first side lobes, whereas they weren't so much for the broadside pointing. And that jostling is evident throughout the pattern. So there is some difference, especially in the side lobes, but the main lobe is not terribly affected. So again, if you're not steering too far away from broadside and you have arrays of this type, the mutual coupling tends not to have too big an effect on the pointing or the precise shape, say the half-power beam width of that lobe. Once again, the active impedances, that's another story altogether. What we now see is the active impedances are scattered all over the place. Most of them are here. The two outer elements are over here and over here. And really the best you could do in terms of impedance matching this thing is trying to choose a source impedance which is somewhere in this ballpark. And you can see once again that finding a single source impedance that gives you a good match to all the elements is quite challenging. So what's commonly done when these arrays are actually designed is to try to figure out alternative geometries and choices of materials that cause all these things to get closer to some value. Not necessarily to the self-impedance, but just clustered in such a way so that even accounting for scan dependence, you get a sufficiently good match. And I'll conclude by saying that the consequences of ignoring this and simply, for example, using a 50 ohm source impedance on your transmitters would be that you would get a lot of reflection, certainly for the edge elements, but also varying degrees of reflection here. And if you're transmitting relatively high power levels, that could be a very dangerous thing to do. But even if you're not operating at high power levels, that is wasting power and reflection. That concludes this lecture on mutual coupling in the transmit case for a ULA.